So the talk today has this title, Elastic Dissipaters. I'm going to talk about highly fatigue resistant materials as a strategy. We all know glass is brittle and metal is tough. The toughness in metal comes from plastic deformation. Rubber always appeal to people as a tough material, but it doesn't come from plasticity. Toughness doesn't come from plasticity. So I'll call it elastic dissipator in the following sense. So when material is being stretched, before fracture, there is no plasticity. When you release the load, the material releases elastically. However, if material is ruptured, all the elastic energy is dissipated. So this mechanism is what I will call elastic dissipator. Now, if you put in the general context of a theory of a fracture, you can think this way. So it's well known, Griffith's theory of 1921. It's almost 100 years of history. Griffiths considered glass as a model material, silica. So here is a glass. Let's say just a simple model picture. You have an atomic bond between these two atoms. So when crack coming along, the crack only need to cut one layer of atomic bonds. All the other atomic bonds remain bonded and material is elastic. As a result, because you only cut one layer of atomic bonds, the toughness is very low. This is an energy per unit area of a crack, just about 1 joule per meter squared. Now, and we all know, if you have studied fracture mechanics, in 1948, Irwin and Orwan had a picture of a high toughness material. They were talking about a steel. So the toughness is on the order of 10,000 or even 10 to 5 Newton per meter squared. So their picture, of course, is a crack growing in steel. But here I illustrated in a ductile polymer, such as a polyethylene. So the point is when crack grow in a ductile material, before you snap an atomic bond, there is a large zone of plasticity, dissipate energy. So dissipation energy in the bulk, that's why you have high toughness. Now, in 1967, Lake and Thomas described a picture of for elastomer. Here's a picture. For elastomer, you have one molecular chain, a polymer, and a neighboring molecular chain. Along the chain, all the atomic bonds are just covalent, as strong as in glass. However, between chains, the interaction is weak. It's typically interact through van Waals interaction or other weak physical interactions. Now, if you have a crack, try to break to if you have a crack, try to break atomic chain, molecular chain. You only need to break one layer of atoms, that's true. However, before you break this chain, the entire chain is stretched near to the covalent energy. So when this bond is broken, the entire chain release energy. That's why toughness is high. So this is a model I would call now the first model of elastic dissipator. So the toughness is on the order of 10,000 joule per meter squared. So this has been known for many decades. So in recent years, myself and several other groups have been trying to create tough hydrogels. So here's one version we published in 2012. So the hydrogel is really very tough. So here is a hydrogel. Hydrogel is transparent. What you are looking at is a black background. So we can stretch this hydrogel to 21 times. You can see 21 times. Very tough material. In order to measure toughness, fracture energy, we also use a blade to cut a crack and then stretch 17 times. The crack does not grow. Instead, the crack become a hole. So this corresponding to very high toughness, this measurement, give us a high toughness of this value. Now this high toughness put things into context. For tofu and jello, the toughness is about 10 joule per meter squared. Most gels have this value. Contact lenses, 100 joule per meter squared. Cartilage, 1,000. Natural rubber without any reinforcement, 10,000. So our hydrogel with 90% weight percent water has a toughness comparable to natural rubber. Very tough behavior. Now, this behavior comes from something like plasticity. So we made our material by a mixing of polyacrylamide gel and alginate gel. Polyacrylamide gel is an elastic gel. So it has, before this chain is broken, when crack comes in, the whole chain is stretched to covalent strength. When this bond break, you release the energy of the entire chain like that. So in this case, polyacrylamide gel, we measured the toughness is about 100 joule per meter squared. This alginate has, alginate came from algae. So you have, it's a biopolymer. This polymer has a negative charge on the chain. And in the water, it's a hydrogel. In the water, you have a calcium ion. And these calcium ion bridge this negative charge. So this is ionic crosslink. When crack come along, it need to break this ionic bond and this ionic bond, but doesn't really break ionic bond in the bulk. As a result, the toughness is low. It's on the order like tofu and jello, 10 joule per meter squared. When we mix these two things at a molecular scale, now when crack come along, before I break this polyacrylamide chain, I need to break the stress is already high enough to unzip many ionic crosslink in the bulk. That's why toughness is high. So toughness need to break polyacrylamide chain, but also break many ionic bonds in the volume. So this is a mechanism we call the brittle plus brittle. Two brittle materials give you a tough material. It's a great magic. We were very happy for a number of years. By now, many people do similar things. However, this material has a problem. The problem is about fatigue. So now fatigue, this is a kind of a measurement many people in the field have been doing for many decades. We are also doing this. So what you do is you prepare a material, cut a crack, and apply cyclic loading. Observe crack length C growing cycle by cycle. So you plot crack extension per cycle. dCdN, N is the number of cycle, dC is crack extension. As a function of applied load, we and other people convert the applied load, cyclic load, to something we call energy release rate. It's standard terminology in fracture mechanics. So, and we just said for our material, if you monotonic load this thing, so the crack extension is very large, one cycle, you already grow to the end. That is a toughness. Monotonic loading, toughness is very high. In our material, it's about 10,000. However, when you reduce the load, reduce the G, the number of cycle become smaller. The extension per cycle becomes smaller as load decreases. So as load decreases more, dCdN become even smaller at some threshold value. Below this threshold value, the crack no longer extend. It doesn't matter how many cycles you cycle this material. This is threshold. For our tough gel, the threshold is about 50. Is about 50. So dramatic increase of threshold. This is also true for natural rubber. For all these decades, people try to enhance rubber. They can increase toughness even more than 10,000, but they cannot modify threshold. Threshold for natural rubber is 50. Our hydrogel threshold is 50. Terrible. So then we begin to study the threshold. Let me just jump directly to a picture, experimental picture. So this is a video. So this is how it looks like. So we have polyacrylamide. This is a polyacrylamide gel, transparent. On the surface of the gel, we mark with a red dye, so we can see the location of the crack. We apply load, cyclic load, up and down. The crack open and close. So the crack doesn't look, it's growing, but it does grow slowly. Let me accelerate this video. So you can see after some cycles, so the crack already grow near to the second red mark. So even this is only for polyacrylamide gel, this very elastic gel. Even for this very elastic gel, it suffers fatigue crack growth. So we try to study this mechanism. Now, this is our tough gel with calcium crosslink and also with polyacrylamide. This is a mixture of two hydrogels, polyacrylamide and alginate. Remember, the toughness of the gel is very high, 10,000 joule per meter squared. However, when we do this experiment without any cut, a tough gel, just do stress strain measurement, but with a cyclic loading. This is a stress plus as a stretch. First cycle loading up, this is the stress strain curve. When you unload, you follow a different path. You have enormous hysteresis corresponding to the unzipping of these ionic crosslink. So when you do second cycle of reloading, the ionic crosslink doesn't rezip. So the second cycle become much lower. And after your cycle go more and more cycles, this is 1,000 cycle, 10,000 cycle, your hysteresis curve just going down and going down. It means you damage this material, unzip ionic crosslink more and more each cycle. So that's essentially what causes fatigue behavior. We further measure this fatigue threshold. We cut a crack into the sample, measure DCDN as a function of a cyclic load. Indeed, the threshold is about 50 joule per meter squared. Remember, this material toughness is about 10,000, way here. So this material is unfortunate. It's tough for the first loading, but it suffers fatigue fracture. This is our tough gel behavior. So at this point, we need some new idea. Now, this is a new idea. We say, how about we do this? We made a material with two elastomer. One elastomer is stiffer than the other elastomer. We call this a stiffer elastomer fiber. So these are fiber. And the compliant elastomer matrix. Both elastomer are stretchable. Now, so if I cut a crack, let's say I mark a material particle by a square. When I apply a load, the matrix is so soft, it can shear dramatically, allow this crack to blunt much more than before. So this is blunt, I call H. Then your toughness will scale with this H. Scale so that the toughness is this opening, and WF is a stretch curve all the way to fracture the area under this curve. So the point is because there's enormous blunting, you deconcentrate stress, spread stress over a long distance of the fiber. In our case, is on the order of millimeter to centimeter. Then, of course, when this fiber break, you dissipate energy over long segment of fiber, H. So that's why your energy is very high. Now, this mechanism is an elastic dissipator because before you have any fracture, this is an elastomer, the fiber is an elastomer, and the matrix is also elastomer. Both materials are elastic. There's no plasticity, no hysteresis. So it's elastic. You can cycle many cycles without fatigue. However, when it breaks, you dissipate energy of an enormous amount, give you high toughness, and by this mechanism also give you high fatigue threshold. So this is our hypothesis. Oh, we tested it by experiment. So here's the experiment we do. We have a material, we make a composite, we make a cut, and do cyclic loading to measure threshold. And then we also measure dissipation, the hysteresis, without any pre-cut. We measure stress, strain curve, loading, and unloading. So if a material is very elastic, so this area, loading and unloading curve, will be very close. So this area WD will be very small. So we measure this amount of hysteresis by a dimensionless ratio, WD over W, meaning this hysteresis area over the entire area underneath stretch curve. So for most applications, you want to have a very small hysteresis, right? Doing loading and unloading, no energy dissipation. However, when crack is extending, you need to have enormous energy dissipation. So that's the ideal material you want. So now this composite really achieve this, this behavior. So here we plot the toughness and hysteresis. We want a material to have a high toughness and a low hysteresis. Now, among elastomer and hydrogel, this unfilled natural rubber actually fulfills this behavior, unfilled. The hysteresis, at least for 20, 30% of stretch, actually all the way to 100% stretch, your hysteresis is quite small, less than 10%. But for all these other material, including our tough hydrogel, the hysteresis, as I showed you, is enormous, and toughness is enormous. Now, for our composite, what we did with the composite, we use two versions of PDMS, stiff PDMS and a soft PDMS. So with this composite, we can easily achieve toughness as high as natural rubber, Now, if you just test the homogeneous PDMS, this is Silgard we're using, the toughness is very low, about several hundred joule per meter squared. It doesn't matter you make it soft or hard, as long as it is homogeneous, the toughness of PDMS is low. People have experience. PDMS is much more brittle than natural rubber. That's common experience. All right, so and then we also made a version of a composite. We use a matrix hydrogel, and the fiber we use PDMS. So here's a fiber and a matrix, and we tested it under cyclic loading. So under a number of cycles and the applied load. As the load becomes smaller and smaller, the number of cycle you can apply without causing any damage. So this is 30,000 cycles. You still have no damage. So keep cycling, no damage. This G is already beyond 1,000 joule per meter squared. So this is a unit of K joule per meter squared. So that's threshold. That's new value of the threshold. The point is, even for natural rubber, the threshold, the best threshold we know about is about 50 joule per meter squared, natural rubber. However, for this composite, the material we use is just lousy material, PDMS, hydrogel. The threshold reaches 1,000 joule per meter squared. There is a lesson. So we keep going. And so we compare with our material. This is a plotting threshold and the toughness. Our material, the threshold is comparable to toughness, right? So for natural rubber and all these elastomer, the threshold is much lower. We already said it's on the order of maybe 100 or 50 joule per meter squared. Even your toughness is very large. various way of enhancing elastomer, for example, carbon black or silica particles, you do not change threshold very much. You can change toughness enormously, but the threshold is still, on the order of 100, less than 100 joule per meter squared. However, our material goes to high value of a threshold. So now the idea is also valid for not just fiber reinforced material. Here we made a elastomer using two versions of elastomer. One, we print one version of elastomer, stiff elastomer, and pour the soft elastomer as a matrix. So this material, so this is a sample prepared. This material is also fatigue resistant. So here is our data, threshold, toughness. This work is here. Also achieve multiple 700 or so joule per meter square for threshold. Enormous compared to regular elastomer. So we feel we have a handle to essentially cure this problem of fatigue of elastomer. This is what you do. You can still have a stretchable material, elastomer, but it's a fatigue resistant. All right, so here's another story related to fatigue. So one idea of enhancing fatigue coming from Lake Thomas model is you increase the chain length. So how many monomers? This little n is how many monomer between two cross links. And so fatigue threshold scale with a square root of n. Then you say why people didn't know this. People, of course, know this. But if you make material with very long chains, your elastic modulus, Young's modulus, will decrease because the Young's modulus scale with 1/n. So there is a stiffness threshold conflict in the material. When you make a material elastomer, you reach compromise. You use some reasonable n. You cannot use very large n to make a material. So here are the data in the literature. Indeed, follows this threshold stiffness conflict. They have a negative slope about 0.5. So 0.5 coming from these two. So this is square root here. This is log plot. For hydrogel, this is even worse because you have 90% water. It still follows this kind of a relation. Now, suppose we do the following. We make a double network hydrogel. So since Jianping Gong made this gel almost 20 years ago, many people study the property of a double network hydrogel. Our group pushed this, we started to study the fatigue of this double net hydrogel. Here's our conclusion. So now, if you only have a single network hydrogel, I just told you there's a conflict. If you choose a chain very long, you have a very small modulus, very high fatigue threshold. So fatigue threshold wins, that's good, but stiffness is too low. If you make chain very, very long, sorry, I probably said opposite. If you make chain very long, fatigue threshold is great, but modulus is low. Now, so you have a conflict. However, if you make a double network, there's a polymer network A, you make polymer network A with a short chain so that you have enormous modulus. And then you have another network with a very long chain, polymer network B, you get high threshold. This double network will have both high modulus and also high threshold. So it's both stiff and fatigue resistant. So here's our data, experimental data of a fatigue threshold as a function of the number of monomers per chain. So you can see as the number of monomers increase, our fatigue threshold does increase all the way to several hundred joule per meter squared. So here is our data of a threshold plotted against the stiffness. I told you all the traditional hydrogel is somewhere here, not very stiff and not very fatigue resistant. However, if make this double network this work, and you push the material all the way to elastomer level, still have 80–90% of water. So that's great. Now, let me summarize the talk today. So this idea, elastic dissipator, started with an elementary picture of a Lake Thomas of individual polymer chain can release the entire energy of a chain. It's an elastic dissipator. You don't need to dissipate energy through plasticity. The consequence of this elastic dissipator is you have low hysteresis. It's very good for application, for many applications. And you can have a high toughness, also high fatigue threshold. I think now we have a handle to win this war on fatigue. So all our work, our papers are posted on our website, and these are particular papers related to this talk. Thank you very much.